Hi, today I'm happy to present our work, Freestyle Training towards Provable Representation Learning on the Spurious correlations and feature noise. This is a joint work with Professor James from Stanford and Professor Linjun from Rutgers, and is accepted by AISTAT23. This is the catalog of my presentation that you might find helpful. So to begin with, real-world datasets are riddled with spurious correlations. As you can see from this figure, we want to classify the color of hair of an image, and the gender is clearly a spurious correlations. A typical ERM model will rely heavily on these spurious correlations and performs bad in test environments where the correlations are broken. The goal is to learn the model in training environments with spurious correlations such that it can perform well in test environments where the correlations are broken, and this is challenging as we do not explicitly know which features are spurious and which are core. Recently, it has been shown that ERM still learns the core features under spurious correlations despite its test performance being bad. What it means, as you can see in this figure, is that if you learn the model using ERM on the training environments, and then you retrain the last layer to reweight different features on the test environments, you can still perform well. This actually opens a new and promising strategy called last layer retraining, which is abbreviated as LLR. The pipeline of this strategy is as follows. So first, you learn the features in the training environments, and then in the test environment, you retrain the last layer, which is actually a linear probe, so that you hope this model can perform well in this test environment. Compared with other settings, LR has its own advantages. So first, it is less demanding and more effective than out-of-distribution generalization, where you are not allowed to use any samples from the test environments. In addition, it is more applicable and computationally efficient than general domain adaptation, because here you only need to fine-tune the last layer, which you can done in a single CPU. However, as we will show below, our understanding to LR is incomplete, and it is not as sweet as we initially thought. So specifically, what we empirically found is that ERM only learns the core features and thus performing well in last layer retraining when the noise of core features is much smaller than that of spurious feature. So if you can see from this figure, the x-axis represents the value of spurious feature noise, and the y-axis represents the value of core feature noise. When the core noise increases or when the spurious noise decreases, the accuracy gain compared with benchmarks actually decreases. So when the core noise is larger, ERM cannot achieve good performance even after you retrain the last layer. So as a result, our goal is to understand when and why the core features can and cannot be learned during training and recovered after retraining the last layer. Specifically, there are two questions to answer. So first, why is noise so important for last layer retraining performance? And second, how to make LR work again under different noise conditions. So why noise matters so much in terms of LR performance? In fact, LR performance is determined by the quality of the learned features. And intuitively, the better the learned features are, the better the performance will be. And in practice, ERM will typically learn a mixture of different kinds of features, both spurious feature and core features. And importantly, the proportion of different kinds of features depend on the trade-off between a feature's information and noise. Features with larger noise are used less. As a result, during last layer retraining, when the proportion of the core feature is small, we will suffer more to amplify this feature, which can explain why LR no longer works in such case. So you can see from this illustrative figure, there are two optimization curves in the figure. One is the red one and the other is the blue one. The red curve is trained when the core noise is much smaller. This makes the ERM model focus more on the spurious features, And as a result, when retraining the last layer, we suffer more from amplifying the core features because now you can see the Spurious feature is simply a noise term. On the contrary, the blue curve is trained when the core noise is smaller. And as you can see, during training, we do not need to suffer much from amplifying the core features because CRM already focused much on it. So to better describe our intuitions, we formalize this into the following theorems. So here we consider a minimum theoretical framework, which is a two-layer non-convex optimization problem. The model is fx equals to x times w times b, where w with shape d times n is the feature learner, and b is the last layer. Our data is generated as using the following mechanism. Here x1 is the core feature and is invariant, and the label is generated by x1 plus a core noise term. x2 is the Spurious feature that is different during training stage and testing stage, and is determined by the label and another Spurious noise term. So these two noises are independent, and they have variance eta core and eta Spurious. During training, we consider infinitely small learning rate such that the optimization becomes a gradient flow. After the training stage, the learned features W is fixed, and we only retrain the last layer B. This can be obtained by a standard LR techniques. So our informal theorem are shown here. There are two parts of our theorem. So first, when the core noise is much smaller, which means eta core is smaller than eta Spurious. Under some assumption for any eta core and any eta Spurious and any time t, we can show that the test regret of LR is upper bounded by 1 plus an additional term times the optimum error. And this term is the ratio between the eta core and eta Spurious. So as you can see, when eta core is smaller, this term is upper bounded by 1, and it is sometimes much smaller than 1. So our test error is close to the optimum error. However, when the core noise is much larger than the Spurious noise, as you can see, then the test error, the ratio of the test error and the optimum error is lower bounded by 1 plus another term. And as you can see in this term, there's still a ratio of eta core and eta Spurious, which is larger than 1, and sometimes it can be very large. So as a result, the LR performance will be quite bad. So after explaining why noise is so important to the last layer retraining performance, we want to improve its performance. So the takeaway from theorem is that features learned in a supervised way are sometimes biased under certain noise conditions because the label will incentivize models to focus on features with small noise, which is not necessarily the core features. So to circumvent this issue, we should also learn features in an unsupervised way. And there are two advantages here. So first, noise in the label mechanism will no longer influence the learning because we do not consider or we do not rely on label at all. And second, this will help us preserve features that are useful in the testing stage but are actually ruled out because they are less informative than other features during the training stage. So to this end, we propose the following algorithms called freeze-stand train, which is abbreviated as FTT. So specifically, we first freeze certain salient features unsupervisedly, which means that we learn a fraction of features in a unsupervised way using whatever kind of unsupervised method like self-supervised learning or whatever. And then we train the rest of features using a standard supervised learning technique such as ERM. It should be noticed that this unsupervised algorithm and supervised algorithm can be replaced to any other kind of similar algorithms. So our FTT algorithm is actually very open and extendable. By combining supervised learning and unsupervised learning, we can show that FTT actually enjoys the following properties. So first, in our theoretical framework, for almost any eta core and eta Spurious, no matter which one is larger or which one is smaller, the test error of FTT actually converges to the optimal error gradually. So this clearly improved the regret bound. And you can see from our previous slides that ERM cannot have this property. And in addition, as you can see in the figure below, compared with ERM in this actual experiment, FTT can indeed learn core features when the inner core is much larger, which corresponds to the left down part of the figure. As a result, it can achieve a better LR performance, having a 10% of accuracy increase. And we next systematically test FTT on various popular benchmarks to show the value of our algorithm. So we first test FTT on Spurious correlation benchmarks. We compared the LR performance of FTT with ERM, IRM, and DRO, as well as JTT on two popular benchmarks, Waterburst and Celebrate A. And to study the influence of noise, we explicitly generate noise by flipping labels, with Spurious noise equaling to 5%, which remains unchanged, and core noise ranging from 0% to 10%. So as you can see from the table, when the core noise is more, all algorithms can perform quite well. However, when the core noise gradually increases and becomes larger than the Spurious noise, the performance of other algorithms degrade much, but FTT remains a quite good accuracy, thanks to the help of this unsupervised learning feature. We further test FTT on more general distribution shift benchmark, VLCS, PACS, and Office Home. So notice that there's no explicit Spurious correlation and noise between features and labels in these three datasets. But however, you can see from the table that FTT still outperforms other algorithms with respect to LR performance, despite it is initially designed for Spurious correlation benchmarks. So this actually implies that FTT has a strong expansibility and generalizability. So to give a conclusion, we empirically show that ERM only learns the core features under certain noise conditions, and we give a theoretical framework to explain this phenomenon, these observations. We found out that noise is an essential factor in this learning process because labels will incentivize the ERM model to use features with smaller noise, which is not necessarily the core noise, the core feature. And to improve LR performance, we propose FTT that combines supervised learning and unsupervised learning. Under Spurious correlation and distribution shift benchmarks, FTT consistently outperforms other purely supervised algorithms, showing its effectiveness and strong extensibility. So our code can be found in the following GitHub repo, and I hope you like our work. And finally, I will be starting CS PhD at Stanford this fall. So if you find my work interesting, please feel free to contact me. And here's my homepage. Thank you.